Okay, so I'm going to speak today about some thoughts that came out after discussions I had with a coworker. So we do a lot of heap exploitation. So we either write exploits for published vulnerabilities or for vulnerabilities we find ourselves. And after we have written a lot of them, we started seeing patterns like things repeated, like both on the allocator side and on the attacking side. So after we saw these patterns, we thought, okay, so since there are patterns there, then we can abstract and we can approach the subject from a point of view that is both easier to understand, because this is a complicated subject, but it's also easier to teach it to someone that is new to this subject. Before I go on, I want to mention that this is work in progress, right? So don't expect like the perfect methodology you can take and apply and write heap exploits from day one. Okay, before I go on, does everybody know what the heap is? You do. Okay, that's great. Do you know what an exploit is? What a memory corruption exploit is? Okay, so has any of you written a heap exploit in the past year or so? Okay. Okay, I'll try to do like an introduction, but I won't go into many details. So if you feel you're lost at some point, just come and find me afterwards and we'll talk about it. Also, if you have a question, just interrupt me, raise your hand and ask me during the talk, right? Don't wait until the end. Okay, so a couple of words about me. I'm a researcher at Census SA. I basically do vulnerability research, reverse engineering, exploit development, these kind of things. Before that, I did a postdoc at Trinity College Dublin. There I worked mostly with applied cryptography stuff, like designing, implementing, and attacking network security protocols. I didn't do any like math, like developing cryptographic algorithms from the math side. Also, I want to mention that these thoughts on exploitation abstraction is basically joint work with my co-worker Huku, who actually would be here, but he's serving compulsory military service in Greece. Okay, just a quick warning. There are no pictures in this talk. There is only one picture, and it's not a cat picture. There are no diagrams, no charts. There is almost no math, though, so just a little bit of math. There's a lot of text, so I promise not to just read the slides. I'll try not to read the slides. And as I said in the beginning, it's a work in progress, so it is always going to be a work in progress, to be honest. I don't expect this subject to ever be completed and have like a tool or like a methodology that you can take and use, right? This is more like a discussion I want to have with people that write heap exploits. Okay, so Alexander invited me to Balkan. I want to thank him very much for his hospitality, Helen as well. And I think that's a great invitation. That Alexander gave me that as an invitation, and it's amazing. I mean, I know you're probably used to seeing it every day, but for me it was something new, and it was amazing when I first saw it. Okay, so that's the outline. I'm going to give a quick introduction to the subject. I'm going to say a few words why I think it's important. Very, very quickly about related work. Then I'm going to try to give the context of heap bugs and a few words about how their exploitation looks like. And then, as I describe that, I'll try to abstract and present to you the primitives that can be reused and applied on other similar situations. And towards the end, I'll give you a small model we have been working on for this abstraction. Okay, so the motivation is basically that heap exploitation is very, very time consuming, and it requires a lot of effort. Basically, before I go on, I just want to tell you that heap bugs are the most common type of bugs, right? So you no longer have like Stack Overflows, like the normal Stack Overflow that we used to have like maybe 10 years ago. These all are gone now. So most probably you will have like a heap overflow or a use after free or something like that. So when you start looking at a bug, you have to understand the allocator that the application is using underneath. So for example, if it is a Linux application, then you need to understand what glibc is doing when the application is doing a malloc call. You need to understand the metadata of this allocator. So the metadata are the data that the allocator uses to do bookkeeping, to keep its organization data. You have to understand the allocator's algorithm. So how does it allocate memory, how it frees it. So is it, for example, a linked list, or is it a bitmap, or these details. One of the most important things is to find out how the application interfaces to the allocator. So, for example, if you send a packet to the application, does it allocate memory? And for example, if you do an HTTP request, when exactly does the application, let's say Apache, for example, allocates memory, and when does it free it, corresponding to the HTTP request you just made? And the other important thing is how are these data that the application is allocating put on the heap? Are they put one next to the other? Does it have like a page and it keeps like a different page for its different request? So you need to understand this. And basically when you look at these things, you have always to have in mind that your goal is to do something that will give you like an advancement towards exploitation. So you either need to do code execution or leak some bytes to have a memory leak and things like that. And of course, all this have to be viewed in the context of complicated bugs, right? So even integer overflows that lead to heap overflows are not that common anymore, right? Nowadays, we're talking about complicated bugs. There are no scarce fruit anymore. Maybe in like very like specific and target-oriented applications like scatters and stuff like that. But in big applications like media players, browsers, stuff like that, it's almost it's very difficult to find a scarce bug. I'm not saying that there aren't, but it's very difficult to find one. And of course, there is constant development by the vendors of mitigation technologies. A mitigation technology, you can think, if you haven't heard the term before, you can think of it like a defense, like a generic defense that the vendor has built into the application system first, let's say, or the target product, Internet Explorer, let's say, that makes heap exploitation more difficult. Okay, so we need to find ways to make heap exploitation faster. We need to save time. We need to understand it more quickly, the bug we have and the allocator we are attacking. And we need to apply this in practice. So my goal here is not to do an academic exercise, not to give you like a mathematical model and show that the model describes some attacks and some allocators and just, publish it and leave it on the library. No, that's not my goal. My goal is to come up with something practical, reusable, and people who write heap exploits can actually use to save time. Maybe not save time, I know that maybe it's like a very optimistic goal to say that, I don't know, like Nico Wiseman will use this methodology to attack a new application, but maybe this methodology will help Nico to describe to a junior researcher some things. That would be an excellent goal for me. Okay, so a couple of words about abstraction. I don't know if you have done any computer science degree. One of the first things that the professors tell you is that the most important skill in computer science is abstraction, and that's true. Abstraction helps you see patterns and reusable stuff like primitives, and it's a great tool to tackle complexity. A similar application in software engineering are the design patterns. If you've done any development, you know this term, design patterns. So basically, design pattern is a solution to a common problem. that has been standardized, and if you have this problem, that's the right way to solve it. Of course, I think that heap exploitation is much more complicated than writing software, but I think that abstraction can help to tackle this complexity of heap exploitation. Now, when I will use the term exploitation again and again and again, I don't mean like XSS bugs or logic bugs or stuff like that. I strictly mean memory corruption bugs, right? So you are able to change memory of the application that you're targeting, you're not supposed to change, right? Some related work. So Chris Valasek and Ryan Smith talked a little bit about what they were calling exploitation blueprint. So basically, they understood the value of abstraction, and they saw that when they were attacking applications again and again and again, they saw that there were techniques that they were using. So they had a talk, I think, in Black Hat Europe 2011, that they showcased some of these reusable techniques. Mayhem did this talk about automated exploitation grand challenge. So he set out like a challenge to the community that does exploitation, and he said, okay, our goal here is now to have like a completely automated exploitation writing apparatus, software or whatever. And maybe not completely automated, but maybe one that requires reduced human interaction. So he went out, he identified categories of exploit primitives, not just for heap exploitation, but for general exploitation as well. But one of the important things in his talk was that he suggested that the heap could be modeled as a probabilistic transition system with a Markov chain. So basically that allowed him to do random walks to reach exploitable states. So that means that if you have like a certain input that can lead to one state and some other input that can lead to another state, you can find like the probabilities that some input leads you through a path that leads you to a state that is useful to you, that aiming to do exploitation. Halvar Flake and Sergey Bradus talk a bit about weight machines individually, I think. So I think Halvar Flake was the first that used this term, and then Sergey Bradus liked it and used it again. So basically, a weight machine, you can think of it like the state machine that describes your target program after exploitation. So the developer, when he develops an application, he has a state machine in mind. But when there is a bug that allows corruption of memory, there are states appearing that he didn't think about, and now the states may be reachable. So that's a weird machine. Matt Miller did a talk about modeling exploitation. So the important thing in this context that I'm talking about today from his work was that he identified that there is a finite set of primitives for transitioning between the states of a target program when there is a memory corruption. And basically, if you combine these primitives that let you jump from state to state, you come up with techniques that can help you do exploitation. Okay, so I will give now a quick overview of what I'm talking about when I'm referring to heap vulnerabilities or heap bugs. So I will quickly describe a heap buffer overflow, a use after free, Douglas tail pointers, and double freeze. So these are the most common bugs. So if you find a heap bug either through source code auditing or fuzzing, it's probably going to be one of these. I mean, if you go down it and understand the root cause. So buffer overflow, it's like a standard thing. You allocate a buffer on the heap, and the developer makes a mistake to the allocation of the buffer. So that mistake could be like from a multiplication between two numbers that are influenced by the user, and then the result could wrap, right? So it will become much smaller than what he was expecting. But then he goes and writes like what he expected to be the output of the multiplication. Also, for example, you may have like a for loop that writes something to an array that you have allocated in the heap. And again, the mistake here would be the size of the for loop. So that basically means that you have a heap buffer and you write to it, but since you have miscalculated the length of the write, you write outside the buffer, right? And that means that you overwrite stuff that are placed after that buffer. The dangling pointer is basically that you have an item allocated on the heap. For example, that could be like an object when you say new class something, and then you have a pointer to that object. That could be like a raw pointer, or it could be like a pointer from another object. It doesn't matter. And then you perform some action, like for example, some JavaScript call or something, that actually frees the heap item. But the developer forgot to, like in this case that you have found, that cause a free, he forgot like to decrement a reference counter, or he forgot to invalidate the pointer to that heap item from the other object or the raw pointer. So basically now you have a pointer to a piece of memory that's now free. So what happens after that is you somehow try to get that slot of memory and place the data of your own. But since you already have the pointer to it, then you can misuse it. Of course, the trick here is that you must find like a construct that when placed there gives you some advancement, gives you some advantage, but this construct has to be of the same size as the one that was freed, right? Otherwise, it won't go on there. So use after free is usually what follows from a dangling pointer bug. So this slot that I was talking about that remained free, but you have a pointer to it. One way to reclaim it is by spraying. So spraying is like, you can think of it like finding a way to allocate lots and lots of memory on your target. So for example, for a web server, that could be like constant requests, one after the other. For a JavaScript, for a browser that supports JavaScript, could be like a constant creation of big strings. Okay, so after that, you reclaim that slot of memory, and you place there something like an object or a vtable pointer. What you should keep in mind is that just dereferencing that pointer may not lead to a crash, right? Because that memory may be unused, but it may be still mapped, right? So it isn't necessary that it will crash. The only way to find such bugs quickly is like if you have some heap integrity tools, like for example PageHeap by Microsoft, which something that is freed is immediately placed under memory protection, so any access to it causes a crash, an exception. Okay, so a double free is when there is a programming mistake and free is called twice on the same memory address. So that's a common mistake. So you have a piece of memory allocated, and if there is some error condition, the developer frees this memory. But then, before the function returns, he frees it again. So if this condition happened, you get to free this memory twice. So this may seem, if you're new to this area, this may seem to you like it's not a problem, but it's actually a huge problem, because underneath you have no idea how what the allocator does when there is a free of memory. So that's why I said earlier that it's very important to understand the allocator. So, for example, a double free may corrupt internal pointers that the allocator uses for base keeping, or on another allocator that has a bitmap that describes which slot is free, which is not. So you can think of the bitmap as an array with a 0 or a 1 in each slot. And this bitmap describes memory and memory slots. So if there is an 1 there, it means that the slot is free. If it is a 0, it means that it is used. So if you have a double free, that means that somewhere that you placed N1, N1 is written again. So in that case, it's not a problem. But in a linked list-based allocator, it's a problem. So let's see now what are some of the common ways that we can use to attack heap managers. These are the 5 like general attack avenues that I have identified. So we're going to see each one, and we're going to see primitives in each one. So when you first go to develop a heap exploit, the most important thing you have to do is to find ways to interface to the allocator. So you yourself, you're like a user of the application, you're not the developer. So you must find that you don't have direct access to the allocator's API. You have indirect access to it, though through the functionality that the application exposes. So for example, if your target is like an operating system kernel, you have system calls. So if, for example, you issue like a write call or a read call or any other system call, what exactly does it happen underneath? Does the kernel allocate memory or does it free memory? What size of memory does it allocate? What size of memory does it free? What structure does it allocate? The same with IOCTLs, opening and closing devices, drivers, APIs. One of the recent, actually not Pangu, but previous jailbreak, version 7, the kernel bug that it was using, it was an IOCTL on the pseudo multiplexer, the pseudo device multiplexer, the PTMX. So basically, there was an IOCTL that was opening that was creating the device that you could pass to it an integer that wasn't validated, and there was an array on the heap that this index was then used, that invalid index that you were passing was then used to index the array. So if your target is a browser, then you have JavaScript, you have ActionScript, Visual Basic Script, stuff like that. So what happens when you allocate a string, when you delete a string? If it's a media player, what happens when we have metadata tags? So for example, if we're talking about an MOV file, what happens when you place an atom container in the file? What happens when you you go through the specification, you understand how the atoms of MOV work, and you try different things, like you declare an atom within an atom within an atom, and you see how the allocator reacts. So basically, you need a way to trace the allocations and the freeze that the application is doing while you have created these test cases, or while you interact with the application. So as I said, if it's Apache, for example, when you send requests to it, or anything else. So one way is to take your debugger, attach it to your target, and place breakpoints at the allocator's mallocs and free functions, and then you log the details when one of these calls is made. Like, for example, the size of the allocation, the return address, or if it's a free, the address to be free. You look at the backtrace of the allocation. That's very helpful if you have symbols. However, this is quite slow and error prone. It doesn't work very well in real big targets. And you get a lot of how can I call it, erroneous output. So, for example, breakpoints may not hit for some reason, or breakpoints may hit and your log may not happen, so that doesn't work very well. What works better is if you take a dynamic binary instrumentation tool, like for example Pin or Dynamorio. I don't know if you've heard of these tools. So basically, these allow you to have like so if your target is binary only, you don't have the source, they allow you to place, basically to hook specific functions or even every instruction of the program and do something when this instruction happens or when the call you're interested in happens. So there are countless examples of how to use these tools. You can do image-based filtering, which is very helpful. So for example, if the bug you're looking at is at a specific DLL, you don't have to trace all the malloc calls of the entire Internet Explorer, right? You say, I'm only interested in the malloc calls of this specific DLL. Generally, DBI tools are quite slow, but what we have seen from experience is that if you spend time and tweak them and learn their internals, they can be very fast and much less error prone than debugging. The problem with most DBI tools is, I mean, with Pin and Dynamorio actually, is that they're just targeting userland applications. You cannot do DBI for a kernel. Now, when we were looking at kernels and tried to do this interface mapping thing, we basically created a kernel module that was hooking malloc and free. And at its call, it was recording all these details we were interested at. We were doing manual stack unwinding to see the backtrace of the malloc and the free. And we were filtering that out based on symbols if we had them. Which in most cases, like Linux or FreeBSD or OS X, you have them. You don't have them, for example, for iOS or stuff like that. Okay, so the previous slide was talking about dynamic, like runtime interface mapping. We have also found static interface mapping to be very useful. So basically, it's very useful to have the sizes of objects, structures, and because, as I said, when you know the sizes of the structures, you can use them in use after free scenarios. So usually when you have a target, you may have source code when we're talking, for example, about a kernel or Firefox or whatever. Or you may, if we're talking about Internet Explorer, you may have like debug info through PDP files. So basically, you pass the source code with something like CLang or whatever, and you pass the debug data for interesting objects and structures of specific sizes. So we have written a CLang tool that does that. It works. I mean, we get sizes of structures and classes and things like that, which is useful. Of course, it doesn't grok all source code, but I hope someday it will. Also, one other interesting thing we have done is with PDP and WAR files is that we have written parsers to get this size of classes and objects through there. So, for PDP files on Windows, we have used this debug interface access that Microsoft provides, which is an API to parse PDP files. And for Dwarf, for ELF Dwarf on Linux, there are countless tools that help you do that. The trick was how to do it for Mako files on OS X that have Dwarf information. So what we have found is this module from LLDB that can parse Mako Dwarf information. And it's scriptable through Python, so that was great. One other thing we have done, and it's very helpful in a situation when you're trying to map how you will interface with the allocator, is okay, so you know that you want a specific size of object, right? And you have found it through the previous means I described. So how you, as the user of the application, lead the application to allocate this thing? You need to find a code path that does that. You have your API, like if it is a browser and you're using JavaScript, or you have functionality like HTTP requests, or if it's a media player, you have the parsing of the metadata. So you need, after you have found those, you need to find code paths from the things you influence to the things you want allocated. So if we're talking about source code, you can do like some simple static analysis to identify call paths. For example, if we're talking about source code, you can do it with CLang. If we're talking about a binary application, you can use IDA and IDA Python. No, that's quite fast. It's not at all slow, but it's quite imprecise because we're not doing any constraint solving. So if we identify a path, we don't really get the constraints that lead to that path and then give them to the solver and try to see how the input must be changed. We don't do that. We just identify the paths and then we write test cases to see if we can hit them. If we want to automate it, then we have to do the full symbolic execution constraint solving thing. But we're not doing that right now. Okay, so that leads us to our first abstraction primitives. I call them interface primitives, and there are these four. It's the allocate, the free, the allocate control size, and the allocate control type. So you have these primitives, and you have your target, and with the methodologies I described, you try to see how you can satisfy this, how these primitives can be implemented in the target you're investigating. Okay, one interesting thing here, I have been reversing lately the mitigations Microsoft introduced in Internet Explorer lately. So basically, they have implemented what they call protected free. Now, this directly breaks this primitive here. So you have identified the path that if you call, if you reach that path, Internet Explorer does a free of a specific object. What Internet Explorer does nowadays is it breaks this interface from JavaScript to the actual free. So when you do a free, it doesn't actually do a free. It keeps a per thread list and places the slot in that list. And then when something happens, for example, when this list has grown too big, actually 100,000 bytes or bigger, it goes and frees them at that time. So basically what this does is introduces non-determinism to this free interface. And it directly breaks primitive number 2. Okay, so let's move on to heap arrangement. So, okay, so you have a buffer overflow, right? And you're able to write data after a buffer on the heap. So the next step is to find a way to place data there that you are able to do an override. That means that when you trigger the bug, the overflow, your heap must be in a predictable state. Sotirov did some work on that. He was calling it heap feng shui, and he was using JavaScript to influence the heap layout of Internet Explorer. So basically, when you're trying to do that, you try to understand the allocator's behavior. So you observe it while it runs, while you throw test cases to it, and you reverse its allocation deallocation functions. So one behavior, for example, is that when you do a lot of frees, so let's say you have a slot here, and a slot here. So you free these, and then you ask back with malloc a slot of that size. So if it is a FIFO allocator, it gives you the first one you have freed. If it's a LIFO, it gives you the last one you freed. So you observe that, right? So you note it down. That's useful information to have. One other thing is that you're trying to force the allocator to be in a predictable state. Because if it is an unpredictable state, you have no idea what object there is after the memory you're overflowing from. One primitive here that has been very helpful is this, I mean, you can even call it like a small algorithm. So this works on most allocators, and it's one of the first things I'm trying, even without understanding the allocator. So you try to defrag it, right? So you do a lot of same-sized allocations. That basically mean that if there are some free slots within used slots, these are all filled, and then you get like a fresh page or like a fresh container of the allocator. And then you continue to do allocations, and these allocations then are most probably one next to the other in this fresh container you got. Now the next trick is that after you have done that, you free every other one. So from this fresh container you got, you free one, then you leave one, then you free one, then you leave one. And then you trigger your vulnerable call. Then this vulnerable call will fall into a free slot, And then afterwards, you have a slot you have filled yourself with something you control. So that brings us to the arrangement primitives. So primitive number 5 is the force contiguous allocations primitive, which basically means that you do that algorithm I mentioned. You do a lot of, you try to find a way to get allocations that are placed next to each other on the heap. The create holes primitive, you try to do holes in that contiguous allocations, and you try to find a way to reclaim a free slot within this holes you created, right? Because when you reclaim that, then the slot after that is something you controlled from the previous step. Now, one other of the mitigations that Internet Explorer has nowadays, and it was introduced like maybe a month ago, is basically something that breaks this primitive number 7. So it's called the isolated heap. And what it does is that the developers went through like previous exploits, and they found like objects that they are used very frequently in attacks. So they say, okay, these objects, we're not going to put them in the same heap that all the other objects go. We're going to create a new heap and put them there. They call that the isolated heap. So basically, that means that when you create your holes, you have placed your structures or objects there, and when you try to reclaim a free slot with something, this will not go where you created your layout, it will go on another heap. Of course, the trick here is to study all these objects that go on the isolated heap and try to do these tricks with these specific objects, right? Which may or may not be possible depending on your bug. One other important thing here is this last bullet here. These two mitigations, like almost all other mitigations out there, like ASLR, DEP, NX, whatever, they shouldn't be viewed like, from a defensive viewpoint, when you want to protect something, you should view these mitigations in tandem. You shouldn't view them one irrespectively of the other. They protect something only when they're all together enabled, right? They offer much better protection. Now, as an attacker, you bypass them one by one, but maybe if they're all enabled at once, you will not be able to bypass one if the other is enabled with the same bug. Maybe you need another bug or something. Metadata attacks. Okay, as I mentioned, heap managers have metadata. For example, these are data that the heap managers use to book heap, to keep, for example, a list of all the free slots or of all the allocated slots, of the sizes that are available and things like that. So basically what you're trying to do in this attack primitive is that you try to corrupt this metadata. So you're using this placement that I mentioned earlier, but you don't try to place application-specific data next to each other. You try to place a vulnerable object that you can overflow from next to some data structure of the allocator. Of course, when you think about it, you may say that, okay, we're talking about like 10 different allocators. Each one has different metadata. But experience has shown that this kind of metadata attacks are highly reusable. And that's an example I'm always giving when I try to describe that. So the original unlink attack against the glibc malloc allocator was documented by Solar Designer in 2000, and it's basically this one, right? So you control this thing here which is the object that is freed from the allocator. And these are the metadata of the allocator. So that points to the previous slot, and this points to the previous slot, and this points to the next slot. So you control this, right? So then the allocator goes and does this unlinking of the double linked list, which is like a normal unlinking of a double linked list, right? But since you control that, you control what you're writing, goes into BK. You control where you're writing it, it goes into FD. And then you have the reference of where equals what. So you have an arbitrary write. Now, this attack was published by Solar Designer, and then after like, I think 7 years or so, in 2007, I think, if I remember correctly, it was patched, and it was no longer working. But then Windows Vista came out, and its kernel allocator was using a very similar design to glibc malloc, and it was suffering the exact same, you could use the exact same attack against the Windows Vista kernel allocator. I think that was patched with an exactly like similar code. It was patched in Windows 7, in the Windows 7 kernel. But up until then, its exploitation was exactly the same. Okay, so the two most common allocator designs is the double linked listing, where the different slots of memory are bookkept through a double linked list. The other common design is the bitmap based allocators. JMalloc is an example of that. So basically, you have arrays, as I said earlier, that represent heap memory. And each slot, if it has a 1, means that the slot memory is free. If it has 0, it means that it is used. Basically, in these allocators, when the allocator is looking for a free slot, it gets a number from its metadata and then uses it to index the array to find the one. So if you corrupt this index, you can force the allocator to return to you another slot than a free one. So for example, one that is used. So if you get back, basically that means that if you get back a slot that it is used, then you can do whatever you want with it, right? So if you do a malloc and the allocator returns to you like a structure that is being used by the application, then it's game over, right? We're calling that the forced return used attack. Right? Okay. Another attack. I will tell you why. Do I mention it? Yeah. Okay. So some years ago, this guy, Phantasmagoria, did an amazing paper called Malloc Maleficarum, where he basically cataloged the attacks that were at that time possible against the glibc allocator. And that was after the glibc malloc allocator was patched for the Solar Designer attack, for the Solar Designer unlink attack. And he didn't give any code, he was just describing it verbally. But it was an amazing piece of work. And people started to understanding and write example code for it and things like that. And most of the techniques that he describes are currently dead. They have been patched. But one of the most useful ones, the House of Force, is currently unpatched. So basically, that's a specific attack against glibc malloc. Glibc malloc has what it calls a top chunk. Before I go on, each chunk, each piece of memory, each slot that I was calling earlier in glibc malloc has some metadata on top of it that describe its size. And it has a top chunk that basically describes the whole of RAM of the machine. So when you do an allocation for some specific size, the allocator goes to the top chunk and sees the size that it has. If the top chunk can satisfy your request, then the top chunk is split, it gives you the size you want, and then it becomes the smaller part that is not used becomes the new top chunk. If it doesn't, if the top chunk is smaller than the size you're requesting, then the top chunk is grown in size, and again it happens what I described, it's split and it gives you the size you want, and then the other half becomes the top chunk. So basically, the house of force describes an attack that you attack this way that malloc works. Basically, you're able to overflow into the top chunk through heap overflow. You change the size of the top chunk and place it at an arbitrary big value. Then, if you have a malloc that you control its size, that basically, as I described earlier, influences the address of the chunk that malloc is going to return to you, since it splits the top chunk, right? So, since you have overwritten the size field of the top chunk, that basically means that you can ask malloc to return you any address you want from the system, right? I mean, from the application that you're attacking. So, for example, the canonical attack against that is you ask for a GOT entry, for example, printf or whatever, and you overwrite that with something. So it returns you the address of GOT, and then you go and overwrite it. So basically, the primitive here is not this thing, right? It's not these 3 bullets here that describe the specific attack, but it is a way that if you can corrupt the allocator's metadata, you can force the allocator to return you any address you want when you do a malloc then. Of course, these have some requirements different for each allocator, but when you're looking to attack an allocator, this is the kind of thing that you should be looking at. Right? So, as I told you, these are like primitives that can be used in a methodology when you're looking for ways to attack. So that brings us to the abstraction primitives. The unlink attack, the one by Solar Designer that was also applying to Windows. The force return used, especially for bitmap allocators, where you force the allocator to return you a piece of memory that it's already using for something else. And the force return arbitrary, where you force the allocator to return you any address you want. Oops. Okay, I don't have a lot of time for this, but let me. Okay, adjacent region attacks, I think I described them as when you place data next to each other and you overflow. The important thing here is that when you're doing this heap layout and you're placing and you're forcing allocations of your target applications next to things you can overflow from, you look for specific things. For example, you look to place their string objects, and through the overflow, you change like their size. So when you read the bug, you read arbitrary memory. Or you place their objects that have vtables. So when you overflow into them, you change the function pointers. So when you call a function of the object, your code is called instead of the normal function pointer. So the general idea here is how do you automatically find interesting objects and structures on the target you're attacking that have this interesting characteristics like function pointers or strings with length sizes, stuff like that. This discussion here says function pointer, but you can replace it with X, right? So X can be anything. So, for example, lately, one popular way to attack browsers is for X to be like a vector object, right? So you go there and you do your corruption of the vector objects and you corrupt its size, right? So when you then use the vector and you ask for, so instead of asking for like 10 to give you like the 10th slot of the vector, you ask for an arbitrary address, and then this is returned to you, and you know what's there, that's a leak. So the trick here is to develop heuristics to find these interesting constructs like function pointers or vectors on your target, and then how to allocate these. The one thing we said earlier, you use static analysis to do that. But I mean, just to describe some of these heuristics quickly. So, for example, what is a heap pointer? What is a function pointer? It's a pointer that points to the text section, right? So if you find like an address that points to the text section, then it's a function pointer. So you note this down. So after you know where this is allocated, you go and find through static analysis a path from something you can influence to this allocation, right? So now you know how to allocate a function pointer or a vector or whatever. So the two primitives from these slides is I call them application-specific primitives, which is like a contradiction, because if they're abstraction primitives, how can they be specific? But the thing is that this is exactly what it is. They're like constructs specific to the application that all the applications have. So the two primitives are the force adjacent region allocation, so you place things one next to each other, and the things that you place next to what you overflow from is something useful, like a function pointer, so you overflow into that. So, okay, so all these primitives, I'll try to go quickly because I think I'm out of time. So how all these primitives we have talked about up to this point form a methodology, right? So you take this, you have them, and when you attack a new target, you try to satisfy them, to see how they can be implemented in the target you're exploiting, or they serve like a teaching corpus for a junior researcher. But the goal here is how to automate this methodology as much as possible. And when I say automate, don't read it like full, like robotic automation. Read it like reduced human interaction. So all this methodology, we aim to automate some of the steps to as much as possible. So the first step for automation is modeling, right? So you need to describe a model for what you're trying to automate. But what happens at the next? So you take, for example, glibc-malloc, right, and you create a model for it. What happens when you're attacking the Windows kernel allocator? The model applies? No, it doesn't apply. So what do you do then? You categorize. You may be able to categorize allocators. So, for example, take all the unlinking allocators and model that. But will this model actually describe the Windows kernel allocator, or will it describe something else? Probably it will not describe it. So will the model be practically useful? I have no idea. So we started thinking along these lines. So our first approach was to model the heap as an array. So basically, heap slots are array elements in this model. Heap reads are array accesses, and heap writes are array updates. So when you say array 1, it's a heap read, and when you say array 1 equals x, it's an array, it's a heap write. How do you model the metadata in this case? You cannot model them with just an array. You have to have another array, like a bitmap that describes the state that the previous array, the one that describes the heap, is in. What happens with complicated metadata? Like, for example, linked lists. How do you describe this with arrays? There's definitely a way to describe this with arrays, but it becomes like very complicated, and basically you need, if you think about it and you try to do this model, you will conclude to this thing. You need an array to describe every metadata variable or pointer that the allocator has. That's not something that is easy to do or fun. So that's our second attempt to describe this, to come up with a model that describes this. We use deterministic finite automata. You can think of them like state machines, right? You have a set of states. You have a set of symbols like an alphabet. You can think of them as input events. And you have a set of transition functions. So a transition function is something that gets as input a state, an input, a symbol, and it gives you out another state. Let me go quickly through this. Okay, so let's go to the example from Wikipedia. I think that will make things much clearer. Okay, so your set of what we describe here, we describe something that takes binary input, so 0 or 1, and the constraint is that the input must contain an even number of zeros, right? So that's what we're modeling here. So our set of states is S1, which is an even number of zeros, and S2, which is an odd number of zeros. That's our input, 1 and 0, the alphabet. That's our start state, S1. That's our final state, S1. And that's our transition function. And transition functions are basically tables, right? We describe to you what happens. So you're in S1 and you see a 0. What happens? You go to S2. You're at S2 and you see a 0. What happens? You go to S1. So that's basically a dynamic, a deterministic finite state automaton. Now, we model in this model, we model the metadata as these transition functions, and the user data, like when the application does a malloc, for example, the heap slots, these are the input, like these zeros and ones in this example here. And now the metadata corruptions are modeled as corruptions of this table, right? So if you're able to corrupt the metadata, it means that you're able to corrupt the transition tables. So for example, you corrupt the fact that when you're at state 1 and see a 0, you go to state 2. You change that, for example, to S1. That's a corruption of the allocator's metadata. So basically, the attacker, through that, controls the state that the DFA is in, the deterministic finite automaton is in. Now the data corruptions, like for example the function pointers and the vector corruptions and things I've spoken about, we model these as corruption of the input symbols, right? So basically you're at state 1 and your model says your input, right, is a 0. So if you corrupt that and it becomes a 1, then you were supposed to be at state 2, but you end up at state 1. So again, the attacker controls at what state and input the transition is applied. So indirectly, it controls where the allocator, what state the allocator will reach. Okay, so I don't want to say a lot of things about this. Basically, dynamic finite state automata have a lot of like interesting. I have another 5 minutes. Okay. Okay. So then I can spend some time. But let me see. Okay. So the interesting dynamic finite state automata have some interesting characteristics. So we can use proof by induction to show that a property we are interested in is true. So, for example, an example of that is that given an alphabet and a DFA, a deterministic finite state automaton, that certain states are reachable. And this is very important for modeling exploitation, because basically exploitation is reaching a state you were not supposed to reach, right? So basically, you can automatically, in quotes, identify which transitions must be corrupted and how, right? And you can use proof by induction to do that automatically. Like, and I don't want to explain what induction is. Look it up. And basically, these things that I described here mean that DFAs are used for automated theorem proving. So that have been used in the literature a lot. There are a lot of examples of this. So basically, there is a lot of work out there that we can take and apply to this model. So currently, that's our proposal of how heap exploitation should be modeled. Okay, so practical considerations. So how did we go of making this DFA model practical? Of course, the solution is not to take the allocator, reverse it, or understand it somehow, and then go and manually do the model, right? That's unrealistic. You may do it once, but I doubt you will do it a second time. So can we automatically come up with a model with this DFA model for an allocator. We have done some work on that. We're using PIN, this dynamic binary instrumentation tool I mentioned. We're calling it Moloch because it sees things. Well, and basically, while your target runs, it collects data like, it observes like the data of the allocator, the data that the allocator is operating on, its metadata, its transitions from different states, and tries to record that. And based on these observations, it tries to automatically create this DFA model for the allocator. Of course, the problem is that since it is a dynamic runtime, since this model is created through dynamic runtime data, it doesn't really provide a fully representative model of the allocator, right? So the input you're providing may not cause the allocator to reach certain states that you're interested in the model, right? So that's, of course, you create test cases that may force that, but you may lose some, right? You may not think of all of them. So the idea then is that once you have like an automated, when an automated model has been produced, then you go manually through your understanding of the allocator and fix it like in some places. And of course the goal is not full automation, right? It's reduced human interaction. There's lots of references on this work. So if you are at all interested in stuff like that, come and find me or send me an email. And I'll send you like 50, 100 papers to go through. Okay, that's it.